we bring these intelligent systems together with our airmen to make a more capable system? In AFRO, we have a strategy for autonomy. What you see in the middle is our vision. We're looking to create intelligent machines that can seamlessly integrate. And I can't emphasize enough that seamlessly integrate with our airmen. Making a team where I have an intelligence system and an airman, they're working together as if, and behaving and functioning as if they were a man-man team, and being able to perform a mission in a very fluid and flexible manner. When we break this down, our vision, and say, so what are the major challenges in order to reach that vision? The first thing is all about how do we demonstrate these highly effective airman machine teams? How do we bring our airmen together, and how do we integrate them with an intelligence system in a fluid manner? And I'll say, and it isn't just about creating an interface. It's about how do we put the system together, and how do we figure out what tasks the system should do, what tasks do we want this intelligent machine, what do we want our airmen to do, and how do we put those two things together so that in the end the performance of the airmen and the machine is greater than either would do on their own. The operations that we engage in are in complex contested environments. So systems that have the onboard ability to adapt and respond to things that pop up in their environment. The picture that I show is a space one, and that's an easy example to talk about, is I have spacecraft flying today, and if there is a solar flare and they are out of comm range, we want those systems to be able to detect that and know how to reposition its solar arrays and its sensors so that they don't have an adverse effect from an aging and reduce the life of our satellites that we have up on orbit. So those systems that can reason about there's a threat and how do I respond and what's the right response for it to have for that situation. We talked about human and machine teams. We also want teams of machines. So where do you pull together machines? What activities, what engagement, where do we bring them together so that we can achieve things that without systems being incredibly expensive and not necessarily homogeneous and have the same capability. And then finally, and I think a lot relevant to the Center of Excellence here, is in how do we ensure that these things are going to be safe and effective when they're operating in anticipated environments and when they're operating in dynamic environments. And I'm going to walk through a little bit of these each a little deeper. So we take that demonstrate highly effective human-machine team and we talk about what are our enduring problems. What are the long-term challenges that I don't know that we will be able to fix, we'll be able to come to a conclusion on, but will keep us in the research environment trying to figure out how do we do this better and how do we make progress in this. The first thing is all about trust between the human and machine. And the word that I point you to is calibrated trust. It isn't about just developing trust between the human and machine, but it's a calibrated trust. So having the right level of trust for that situation at that particular time based on the history of that team working together. So it isn't about just trusting it, it's about how do I get the right level of trust for what's going on. The second enduring problem is making sure that we develop that common understanding and shared perception between the humans. If I want them to work together as a team, they have to understand what is the other thinking, what is the other doing, and what's going on that in an anticipatory manner that maybe would help improve the operation of the team and improve the mission effectiveness of the team. So sharing, understanding about things as much about the external environment, what's going on in that mission. But now let me back that off and say, well, if it's a team, then I also need to know something about how is each system of the team working together. So think about, I can monitor my computers today and I can tell what the draw is on them and how well maybe this robotic system is performing. Now let me talk about the same kind of managing and measuring performance of my airmen. How do I know if my airmen has got a good night's sleep and that they're functioning at the right level? And if I want to bring this team of a machine together with that airman, that machine is going to need to know something about the performance of the human at that particular point. And then finally, it's about creating an environment for that flexible and effective decision making. So enabling people to get beyond having to learn how to use a keyboard, to use a joystick, and how do we create an environment that is a little more natural for that interaction. In our, is there a build? Yeah. So under our goal of coordinated teams of machines, it's really about then creating the intelligence on board a single machine to be able to do things and react and respond both in the environment as well as in a larger team. Pulling the systems together so that they can operate as individuals, they can come back, share information, replan, readjust, and then go out and continue to do whatever the mission was. And then underlying that is really ensuring, for that to happen, there has to be a reliable, secure, and interoperable communication. So making sure that the systems know when they can communicate, what do they communicate, what's the priority of information that needs to be communicated, and being able to do that in a secure manner so that they know that it's trusted information. In the complex and contested environments, again, this comes back to systems that have the ability to understand what's going on in their environment, allows them to make sense of the situation so that they know what the right response is. So for instance, if I have an aircraft flying, and it has a mission and it has its trajectory, and all of a sudden there's a pop-up threat that makes a certain area that it was going to fly through an area where it's not safe, it would not be survivable. It needs to be able to understand that and to know, based on the mission it's performing, how does it readapt its flight trajectories to be able to survive and be able to protect itself. And then finally, when we talk about test evaluation, verification, and validation, providing some of the technologies that allow us to ensure that the systems that are making decisions are making the right decisions, and that we can get the level of assurance that the machine intelligence is going to make the proper decision in that space. That we have architecture systems that allow us to do the verification and validation up front so that we're not continually spending money on the upside of design, where making sure that it is verifiable becomes more expensive. And then the other two areas that I'll highlight here is and making sure that we set up these systems so that we can actually verify, we can test out what is that that machine interaction going to be. I want to build up these teams. Now how do we actually put these teams together and verify that the performance of them is improved with the two of them together so that we can maximize our operations. And similarly then, in the case of if I'm going to have teams of machines, how do I build up and test out the performance measures, the performance of a team of machines? So I want to hit this last one a little bit more because I think pertinent to the Center of Excellence here, as well as is a humongous challenge across the DoD, is spending and figuring out how are we going to verify and validate these systems. And so if I look at today, we have complex software systems that are flying today. We have complex software systems that we get in and we drive when we came here today. There is a tremendous challenge in being able just to verify and validate a complex software system, of being able to test out and ensure that the lines of code that are written on today's complex software systems are right and are working properly. If we're looking at tomorrow, now all of a sudden I'm going to start talking about autonomous systems, systems that make decisions. So how do I test and verify a system that makes decision? It's a complex software system, but now it's doing things like decision making. That becomes a whole nother problem because of the state space explosion, the unpredictable environments. I can't test it in the environment completely because I don't know exactly what that environment's going to be. And we talk about the human-machine communication. How are we going to make sure that when we have dropout, that when these systems come together, the decisions that have been made are the right ones and that they can be integrated when they come back together. And just to add to the complexity of that, and then in the future I'm going to talk about systems that learn on their own. And in doing that, they're going to develop their own behaviors and their own decisions. How do I verify and validate that what they've learned is correct, that the decisions that they're now making is correct? And so this complexity, as we go from where we're at today to a future of learning systems, is only going to become more challenging and more of a continue to figure out how the research and how we're going to deal with these systems. And so what I put on the I guess as you're looking at it, the right side of the chart, is 5 of the areas that we've kind of built down that says, so what are the areas that we think are investment opportunities for us to work our way through the complexity as these systems grow. So the first one is about compositional case generation. And that is about enabling that we can reuse software evidence as building blocks as we build these systems. So for instance, if I build an algorithm today that does ground collision avoidance on my aircraft, I really want to be able to use that in a future aircraft and in the same way. I don't want to have to go back and re-verify and validate all aspects of that, only the safety critical ones that haven't been worked out initially in the first instantiation. The real-time monitoring and mitigation of undesired decisions and behaviors really gets into, can I put bounds on the decisions at a higher level architecture so that I am ensured that the decisions that are being made are proper. And when the system starts making decisions that are outside that bound, there's the ability to kind of clasp and control it and keep it in the space that we are comfortable with the decisions it's making. What we would also highlight is that in order to get to these systems, what we don't do well yet, as well as we will need to, is deriving their requirements and doing the analysis on the requirements so we can design the systems to really be insured and be able to make them be viable as we build them out. And using the evidence that we generate during the design in order to become traceable, that shows how the system that we're building out and the architecture that we're building out has been developed from those requirements. And then finally, the last part that we are looking at is how do we use the cumulative evidence? In today's world, we do research and we come up with research data, which shows that the systems work. We then do developmental testing, we then do operational testing, and usually in each realm, that data and the analysis that has been done does not get carried through. So how do we do that so that we are not spending an enormous amount of time and money retesting the things that we feel like we've already demonstrated? Wanted to give you a little bit of a highlight or a little bit of a vision of where we're heading in AFRL for our overall autonomy roadmap, just to give you some context of where things are going and a vision of where we think are coming up next. So if we look at the world today, we are fielding technologies like collision avoidance. We are fielding technologies that allow this PEDSED that I talked about to be able to allow that to operate more efficiently. We can argue that these technologies are more automated technologies than maybe autonomous, but what they are doing is they are creating an environment that allows us to test out some of our V&V tools, allows us to test out some of our theories of how to build up architectures. And in the case of collision avoidance, the significance of that is that it is an algorithm that when a pilot is flying an aircraft and they become locked on something on the ground and they forget that they're flying their aircraft at a very high rate into the ground, this algorithm will jump in and it will take control of the airplane and it'll level out the airframe and pull them out at a 5G turn. That technology, that ground collision avoidance technology, was fielded about 1.5 years, 2 years ago. It has already saved four lives and 4 aircraft. That has made its way through the Air Force. In the pilot side of the Air Force, there are pilots now who used to turn off algorithms like this when they got in the cockpit, who are now asking, when can I get it on my other airplane? I think that is a significant thing, because what we have done is we have an algorithm that is taking over the flight of the airplane. That is a significant first step, I think, in allowing us to now put other technologies on board that allow for some of the operations to be done and handled by an algorithm, by a computer, and doing it in a way where we are invoking that trust and we are invoking the interest from the user, from the operational community. Where we're headed next, though, is looking at now, how can I create teams of manned and unmanned assets? So we're looking at an unmanned wingman to team it with our manned aircraft. So think about taking up a manned airplane and giving him a little unmanned teammate that he can task, he can have it go do missions that maybe he wouldn't want to put himself into those kind of threats. In order to do something like that, you can think about that collision avoidance software that I just talked about is going to be critical, but it's not just now about not colliding with the ground. It's about how do I put an unmanned vehicle up in the air and make sure that it can fly with a manned aircraft and do it in safe manners. How do I put that unmanned aircraft up there and make sure that it can fly and it can fly itself so that the pilot, who is already very busy flying his plane and doing his mission, isn't up in the air just remotely piloting another vehicle from his cockpit. So there's a lot of work that we are looking at to be able to build this wingman that can go out and extend the reach and be able to do things for our manned aircraft. In the intelligence side of that, what we're looking at doing is creating intelligence behind that system that really starts pushing out on that real human-machine teaming. So how do we create an agent behind the analysis of this intelligence data to be able to support the analyst, so that if the analyst's eyes are watching some activity on their screen in one portion, but the automatic tracking algorithm says I'm seeing something down here, eye tracking sensors say you're not looking where I think there's something going on. Now put some intelligence behind that system that says I think I need to get your attention down here. How do I do that right? Or how do I at least mark this so that you can go back and relook at it once what you're looking at calms down and your eyes start wandering around other portions of the screen. But the idea then out in the future is now how do we start integrating these kind of technologies so that we can create this integrated effect, so that we can have ISR, we can have our intelligence collection going on, we can have our weapons on cue, and we can make decisions on what to do as efficiently and fast as possible, again, so that we can operate inside our enemy's decision chain. In order to do things like this, you can see the challenges that we've identified. Significant in that is how do I put these teams of machines together? If I'm going to have this, in the case of this unmanned wingman, if I'm going to have it go out and do a mission and it's going to be out of communication, when it comes back, how do we recouple that manned vehicle with that unmanned vehicle to bring both up on what's been going on and what did you do, and how do you do that efficiently so that you don't have a degradation of overall mission performance? The second bullet talks about machines that execute commander's intent. And you'll hear the phrase commander's intent thrown out a lot, but I'm going to say I'm not certain we actually know what that means. Commander's intent sounds very simple when you're talking about a commander standing up in front of a force of people and saying, here's what I want you to go do. What goes on in our heads and what we understand from that is a pretty complex understanding. When we start talking about that and doing that with machines, whole nother world and a whole nother level of how do we convey intent to a machine. To give you an example of that, we had a group out at an Air Force exercise last week, and they do mission planning. And they literally use a whiteboard and paper, and they stick these papers up to try to coordinate who's flying where, and when do you land, and when do you take off, and where do you loiter, and when do you do this, and who calls out what, and they have a whiteboard full of paper. My digital teammate is not going to understand what's on that whiteboard. So how do we get that off the whiteboard? How do we build that into the system? And then again, how do we convey the intent of what it is that we really are trying to do? And I think with that, hopefully that gave you a sense of some of the challenges that we're looking at. I didn't get the chain, so.
For questions, if anyone has any.
Hi, my name's Mike Bender. I'm the director for the Lab for Analytic Sciences over in Raleigh. I have some experience with AFRL, and one of the things that you mentioned really resonated with me, and it had to do with the decision support of complex behaviors and how they might emerge as the mission planning is taking place. Have you given any thought to how you would deal with the emergence of unintended behaviors and how you would recognize those prior to the behavior actually taking place?
So in my mind, that's where we come back to the idea from our V&V is how do I do runtime assurance? Because I really don't care about emergent behaviors that are within the bounds of acceptable. You know, emerge all you want in that bound, but once there's a behavior that kind of goes beyond that bound, I don't want it to take action on that until I have the opportunity to really, I'll say, verify that that was actually, that's an okay emergent behavior. So in the idea of this unmanned teammate, what we're looking at is those are the kind of, there's things that I want it to learn and be able to do. Let me try this. There are behaviors I want it to exhibit in the air. It's not that I don't want to learn, and I don't want it to learn, but I'm not going to let it do that in the air. I'm going to do all the learning, and where I can, on the ground, where I can verify and validate ahead of time, and then ingest those new behaviors as quickly as I can.